Hello listener, I am Dr. Shongita Das, Assistant Professor of Department of Physics, Brunel University. Today in this video lecture, I am gonna talk about the photoelectric effect. So before going to the main topic, I am going to give some historical background of this phenomena. In early ages, one of the most debatable topic was the nature of light. That means whether light has wave nature or it can be explained using the particle properties. Now, in the year of 1887, the Maxwell's electromagnetic theory as well as the experimental investigation done by the Heinrich Hertz strongly evidenced the wave aspect of the light. During his experiment, he generated and detected the EM waves, and in connection to this experiments, he observed one of the remarkable observation that where he observed that the high voltage sparks across the detector loop, and it was enhanced in the presence of ultraviolet light. If I say in simpler words that when this metallic surface is exposed to some incident radiation, and this radiation has sufficiently high energy, then the photoelectrons or the negatively charged particles are ejected from the surface, and this ejection of electrons are known as the photoelectrons, and this phenomena is known as the photoelectric effect. This is the schematic diagram of the experimental investigation, and this is the photosensitive metallic surface that act as a cathode. And in this vacuum chamber, another metallic plate was present, and that is that acts as the anode, and this is connected to some battery. Now when the incident light is fallen on the metallic surface, then electrons are ejected from the surface and that are collected by the anode or the collector, and a photocurrent is generated in the circuit. Now, if I look the experimental observation, then if we increase the intensity of the light, then the number of photoelectrons or the photocurrent increases linearly, and it implies that the number of photoelectron per unit time is directly proportional to the intensity of the radiation. Next, the effect of potential difference of the anode with respect to the cathode. If the anode is made more positive with respect to the cathode, that is, if the collector potential is increased, then the photocurrent will also increase, and after some time it will saturate. Now, if I go to the this part of the graph, that means the if we reverse the polarity of the battery, that means the anode is now connected to the negative terminal side of the battery, and the cathode is connected to the positive side of the battery, then the photocurrent, and if we made it more negative, then the photocurrent will decrease and it will become zero for a particular potential, and that minimum reverse potential for which the photocurrent becomes zero is known as the stopping potential, and this stopping potential is related to the maximum kinetic energy of the photoelectron, and this is given by this equation, that Kmax is equal to the electronic charge multiplied by the stopping potential. Now, it is also observed that this stopping potential is also a function of the incident radiation, that is of the frequency. Now, if we increase the frequency, the stopping potential will increase. And if I plot a graph between the frequency of the incident radiation and the corresponding stopping potential for different metal, then we observe a linear graph, and all those linear graph, and those will have the same slope, but the cutoff, but the intercept on the positive on the x-axis will be different. That means that there exists a certain minimum cutoff frequency for each of the photosensitive material. That means there will be no photocurrent observed if the incident radiation is not greater than the threshold frequency, whatever be the intensity of the light. That is, it is independent of the intensity of light. Now, all these experimental observation was tried to explain using the classical wave theory. Now, according to classical wave picture of the light, it is known that the incident light, when the light is incident on the metallic surface, the energy is absorbed by the electrons. And if I give a greater intensity of radiation, then the amplitude of the electric and the magnetic field will be higher, and as a result of this, the energy absorption by each of the electron must be higher. That means the maximum kinetic energy of the photoelectrons is expected to increase with the increase of intensity. And also there it cannot explain the presence of any threshold frequency. And also if I incident a low intensity light, then photoelectric effect may be observed after a long time, but it is observed in case of from the experimental observation, that this photoelectric effect is instantaneous. So all these experimental observation cannot be explained through the classical wave theory. In 1905, in 1905, Einstein gave his theory of photoelectric effect, where he gave a different picture of the radiation. He explained that the radiant energy is actually built up of quanta, and or quanta of energy, or known as the photons. And when the the light is incident on the metal, then these photons interact with the electrons, and the quantum of energy is actually absorbed by the electrons. And also, the if the quantum of energy is absorbed is exceeds the minimum energy needed for the electron to escape the metal surface, then the electron is emitted with its maximum kinetic energy. And here this is the equation of Kmax is equal to h nu minus phi 0, and this is famous Einstein photoelectric equation. And in previous slide I already have told you that Kmax is equal to ev0, so it equal to h nu minus phi 0. And also if the kinetic energy is positive only when the h nu is greater than phi 0, so it can explain the presence of a threshold frequency. And so Einstein theory of photoelectric effect can explain all those experimental observation, and for this phenomenal work he was awarded Nobel Prize in the year of 1921. And this gives the particle nature, photoelectric effect gives the particle nature of the light. Thank you.